Today I'm going to go through the January 2024 Unit 1 exam for the Physics International Edexcel A-level exam on mechanics and materials to help students who need to retake this paper in May. So the next exam for Unit 1 will be next week on May the 10th. So if you're taking this paper, you may want to go through these answers. Okay, it's going to be a quick run through due to time commitments. Okay, the first question says, which of the following is an SI unit for stress? Well, stress is force over area, so you automatically know it's newtons per square meter. So that means the answer is D. So you just need to know that. The next question 2, which row of the table contains vector quantities? Well, so I've just ticked a few vector quantities and I can see only A has vector quantities, and I've put a couple of X's where you know they're not vector quantities, so only A can be correct. So you need to know what vector quantities are. Okay, so that's just revision you need to do. Spring is stretched by applying a force of 3 newtons in question 3. The elastic strain energy, which is half Fx, yeah. The elastic strain energy stored by the spring is 0.04 joules. So that's the E, so we know E, and we know F. And they're going to presumably ask us about X. Well, which of the following expressions give the extension in meters of the spring? So you've got to make sure you're using SI units. Well, we got newtons and joules, so we are. So put the numbers in, 0.04 E equals half F 3.0 times X. Change the subject of the equation. As shown here, you'll see X equals 0.04 times 2 divided by 3. So the answer is A. Okay. First 3 questions done. Question 4. It says, just making sure that I'm aligned with the camera. So question 4 says, just getting the alignment just right so I don't have to change it each time. Cyclist moves along a horizontal road at a constant speed. Okay. She then moves at the same speed up a hill with a constant gradient. So first, obviously, all her power goes into the velocity, force times velocity, her pedaling power. Okay, so the only thing that will be acting against her will be air resistance, if there is any. And then she's going uphill, so there'll be part of the gravity acting against her as well. Which of the following graph shows the power output of the cyclist varying with time? So initially, she's traveling along a road, so her power should be constant because she's going at constant speed, and power is directly proportional to speed. So we're looking for a constant. Well, this is constant, but it's showing 0 power, so it won't be A. This one's constant, so it could be B. This one's constant, so it could be C and could be D. So this is initially could be any of them. But when she moves uphill and she's going at the same velocity, I think it says, she moves at the same speed up a hill. She's then also, her power must increase because obviously she's going up a hill because power is force times velocity. And this time she's acting with a bigger force against her. So since V is constant and gradient is also constant, power will be constant. So the second one, the power should be increased. Well, that means it can't be C, and it should be constant because the gradient is constant and she's going at constant velocity. So it can only be D. Okay. Next question is question 5. It says a student dropped a table tennis ball, and the ball so initially was 0. Dropped means he's just fallen out of the hand, not with velocity. The ball fell for time t and had a velocity v just before it hit the ground. So here we got the final velocity is equal to v, initial velocity is 0. The student uses the equations of motion to calculate t and v. These equations ignore air resistance, so telling us we ignore air resistance. Which row of the table shows how the actual values compared with the student's calculated values? Okay, So obviously if you're ignoring air resistance, the table shows how the actual values compared with the student's calculated values. So if you're ignoring air resistance, then obviously the time would be greater than calculated, the real time. Okay, so we're talking about actual values in the table. So this is T actual. So time would actually be greater than calculated because obviously there is some air resistance which will act against you, so it will take longer. And the velocity will be less than calculated, so it can be this or this. Therefore, C is the correct answer because it has 2 ticks. The next question is about a length of string attached between 2 posts and being weighed down by a bird. Okay, the weight of the bird stands on the middle of the string, causing tension in both sides, and because it's in the middle, the tension will be equal. The angles being given, the string makes an angle of 80 degrees at each post as shown. So over here this will also be 80 degrees, this will be 80 degrees by similar angles. So if you resolve, you go T through the angle is T cos 80, so 2 lots of T at cos 80 to the vertical, so we want to resolve up and down, so we're resolving vertically. 2T cos 80 will equal the W. So they want you to work out T, the answer will become C. Okay, so this is about resolving. That's question 5 and 6 done. Question 7 is again about a spring. A force is applied to the spring. Here's the applied force. The graph shows how the length of the spring varies with applied force. Okay, so normally if it was Hooke's law, you'd take off the original length and the axis would move there and you get directly proportional. It would then be force equals spring constant, stiffness constant times the extension. So if you change it, the extension would be from here. So this would then be extension if you did the graph where the dotted line is. They want you to say which of the following gives the stiffness of the spring. Well, the stiffness here would be the gradient, and the gradient doesn't change if you move the axis. So we're talking about the one that says the gradient of the graph. Okay. Question 8 then goes on to a solid cube of weight W is made from a material with density rho. Okay, so if it's a cube, that means the volume of a cube is L cubed. Yeah, 3 sides of length L. Which expression gives the length of each side? So we know that W is equal to density times volume times G. Okay, so that's the mass times gravity. So then you change the subject of the formula, you'll see L cubed must be equal to W over rho G. So this is a cube root. The answer is D. Okay, hope you can see that little 3 over there on the video. That's question 8 done. Question 9. A force is applied to stretch 2 wires P and Q until the wire breaks. So the wire obviously breaks at the end because there's no more data. Each wire is made of different metals, yeah, or of a different metal. I misread it myself. Of a different metal. The stress-strain graph for each wire is shown. So stress-strain, the gradient of stress-strain in the linear part is Young's modulus. Remember, Young's modulus is symbol E is equal to stress over strain. So that's something that you need to make sure you know. The equations are given to you. Which statement is correct? Okay, so one of them is correct. P has a greater breaking stress than Q. Well, if you look at that, it doesn't. Yeah, that's where they break. P is less, and then obviously Q is the opposite. It says P has a greater breaking strain than Q. P has a greater strain, Q has a greater strain. So the ultimate breaking strain is here, so Q is greater. It's both greater in stress and strain. So both of these are wrong. And P, so if you don't know, the answer is C. Okay, the yield stress is this point where it's kind of at the end of the, where it goes beyond the elastic limit. Suddenly you put a little bit more stress on it and the particle yields, it gives way. So yield means to give way. yeah? So it gives way at a certain stress, and it suddenly then stretches. So this is where the yield point is on both graphs, and P's is greater than Q's. You can also work out that D is wrong, yeah, from what I told you, the gradient. It says P has a lower Young's modulus. Well, P is steeper, so P has a greater, it's not lower, P is greater as Young modulus than Q. Okay, so you can work it out by process of elimination, even if you didn't know what the yield stress was. Okay, so that's question 9 done. Question 10, an object moves from rest. So again, u equals 0 with uniform acceleration. So a is constant. And for all these equations, the constant acceleration formula, it's always constant acceleration. Otherwise, you can't use them. And for a time t, so they put acceleration as constant over a time t. The acceleration graph, a time graph is shown. Yeah. X is the area under the graph. Well, if x is the area under acceleration graph, x must be a times t because it's the area under the graph, and a times t is obviously a velocity. But all you need to know is x, the area under the graph, must be equal to a times t because it's a rectangle. So which expression gives the distance? Well, distance for a constant acceleration formula you could use is s equals ut plus half at squared. Initially u was 0, so this bit goes out, that becomes 0, so you got half at squared, and we know from the graph that x is at, so we can take at out of the t squared, so half at times t is half x times t, so you're looking for a similar one, which is d. Okay, that's the end of the multiple choice questions for this January 24 Unit 1 paper. Okay, we'll go through a few more questions. So, a student applied force to a rubber band. This is a 1-mark question. So, the student measured the corresponding extension as the force was increased and then decreased. So this is the increasing force, this is the decreasing force. Now, when you're increasing it, it has a different shape when you're talking about rubber bands. And this is often done in GCSE as well. And when you do this with your rubber tires on a car, each time you're stretching it and then letting it go back to its normal shape, yes, returns to its normal shape, you're going through what's called a hysteresis loop, and energy is stored in the rubber in the form of heat. So basically, each time you go around the loop, your tires get hot. So that's what's happening. And obviously, force times extension, each of these areas is a certain force times an extension, and work done, or energy stored will be equivalent to how many squares you got inside the loop. But first it wants you to know how the graph shows that the rubber band deformed elastically. Okay, now deformed elastically means exhibiting elastic behavior. Okay, so it's showing that it's elastic behavior, and it's because it's gone back to its original length. At the end, when you remove the force, it's gone back to its original shape. When the force was removed, the rubber band returned to its original length or original shape, or the extension went back to 0. Oh, you can't see my answer. Okay, so there's my answer. You can stop the video. So by saying deformed elastically, it did deform, but it reformed, if you like. It's not deformed plastically. So if they say deformed plastically, it means it won't return to its original shape. But you haven't gone beyond the elastic limit. You've stretched it, you deformed it, but then it comes back to its normal shape. So you're within the elastic limit of the material. Okay? If you go beyond the elastic limit, like in the multiple choice question we did, it will then give way, and something internally will change in the molecular structure. Okay? That's question 11 done. That's question 11 part 1. It then goes on to do you've got to do the maths. Work done on the rubber band as the F is increased is greater than the work done by the rubber band as decreased, which was, I was saying, area inside the loop under the lines. The area under the lines is the energy stored, yes, or the energy required to do the stretching. So obviously what I put on here on the graph, I've shown you that here work done by stretching the rubber. So the force is doing the work on the rubber, but when you're allowing the rubber to go back, now the work's done by the rubber, so it's kind of giving you that work back again to the material. But the area inside the loop is what's stored as internal energy of the molecules. Basically, they get hot, okay? And this is called hysteresis loop. You need to make sure you understand the behavior of a rubber. It's different from metals, okay? There's a difference in these values because heating occurred. So I've explained that to you. Determine the energy that caused heating as F was increased and then decreased. So as I've explained to you, and if you know the theory, the 3 marks is you need to know that first of all, that the area under each line is work done. And it could be done by an applied force, or it can be done by the rubber returning to its normal shape. But therefore, the area of the loop between the 2 lines is the energy that is then kept by the rubber in being stretched and then being released again. Now, you have to estimate that inside this loop, and I'm not going to do that because it takes too long, how many of these square centimeters there are. Now, you know this is half a Newton, and you know this is half a centimeter. So you know basically how much energy one of these is. It's a specific energy, because remember, energy is force times distance. Yeah, work done is force times distance. So the energy stored will be the number of squares that you can estimate inside the loop. So basically you have to estimate the number of squares in the loop. The mark scheme says it's 19, yeah? And if you look at the mark scheme, here it is. So they're telling you what they're giving the marks for. Indication that you know is the area under the force extension graph, and the area between the 2 lines determines the energy stored as heat, okay? So this will become heat in the rubber, and then you can work out that the energy is about 0.048, and as long as you're within that range, they will give you the mark, and they've shown you that 1 centimeter is approximately equal to 0.5 newtons times 0.005 meters, which is each of those 1 centimeter squares is 0.025. They've estimated to be 19 centimeters squared, and you see this is an approximate sign. If you get to within approximately 19 centimeters, you can then do the maths. Okay, and that's how you get the 3rd mark. So that's number 11. Number 12 shows a dartboard. In a game of darts, for those of you who do not play darts, you throw the arrows, as they're also called. These pins go into the material of the board, so that they're thrown towards the dartboard. The darts hit the dartboard as shown. Looks like they've gone in pretty straight. A dart is thrown with a velocity of 15.6 meters per second at an angle of 5 degrees to the horizontal. Okay, so it's a projectile question. The dart travels a distance d, yeah, so the distance they're standing away from the dartboard as shown. It's not to scale, but they're giving you the data, so you know the initial velocity is u, you know the angle, so you can use your trigonometry to do whatever you need to do to solve the problem. So just before the dart hits the board, it's at the maximum height, okay? The vertical component of the velocity is 0. So vertical velocity here is 0. So basically, you've reached the maximum height that it's going to go. So if it continued going, it would then start coming back down again, because obviously it's not going upwards, because the vertical velocity at this point is 0. Okay? So given vertically, so they want us to, again, air resistance is negligible. So to do these problems, you need to eliminate air resistance, otherwise it becomes too complex. And you have to remember that physics is the simplification of reality. Okay? You can't always solve these problems if you don't simplify it. All right, so once we know that, they want you to show the time taken to reach the maximum height. So we know vertically, the initial velocity vertically is u sine phi, because you're going away, you're going upwards, so it's a very small amount, and sine phi is a small fraction. Okay, you just need to know that if you go away from the angle, it will be sine. If you're going through the angle, so you want to go horizontally, then it will be cos. And if you don't know that, you just need to go and revise. I'm not going to go through the maths with you. So vertical velocity is 0, and acceleration is against up, so down is minus 9.81. And you want to work out t, so you can use v equals u plus at. Change the subject of the formula to t. I like to do that. It's neater. So then you get v was 0 minus u divided by the acceleration, which is also negative. You can have a negative minus a negative, and the answer comes to 0.139. If you're using 3 significant figures, you probably should use 2 or 3 significant figures, because they're giving you 3 significant figures here. So you could also say this is approximately equal to 0.14 seconds to 2 significant figures. I think both would be acceptable. Okay, so that's question 12a. 12b then says calculate the horizontal distance, where now the horizontal distance would be the cos part, so the vertical velocity would be cos times 5, because you're going through the angle, yeah? So remember, this is the initial angle that we're going, so this time we want to work out this side of the triangle. So imagine we're going this way, this is vertical velocity would be upwards, it's a smaller one, and this would be the cos. So cos is this way, and sine is upwards, okay? So we're using the cos resolution of the vector horizontally, and horizontally there is no air resistance, so it's going to go at constant speed. You know the time of the flight, multiply the horizontal speed, it's not going to change by that, and you get 2.16 if you're doing 3 significant figures, 2.2 meters if you're doing 2 significant figures, and that's how you get question 12. Okay, question 13 is a toy called a Cartesian diver. So this is the diver, this bit here. Yeah, it's a tube. Inside there's some trapped air and some water. Okay, so the Cartesian diver is inside a plastic bottle full of water with a cap on it. The Cartesian diver consists of a tube closed at one end. As you can see, the top's closed, air is trapped inside, as shown. Okay, so this is you may have been shown this by your physics teacher. The student squeezes the bottle. So if you squeeze the bottle, what's going to happen? More water is forced into the tube. Exactly. So you're pressurizing this layer of trapped air inside there, and the volume of the trapped air decreases. That means the density of the air inside there will decrease. Okay, so I'm just thinking when I'm writing these, that's why I'm underlining it. Active reading allows you to take in the question better. Explain why the Cartesian diver accelerates downwards. Well, you know acceleration is a sign of Newton's second law being applied. That means there must be an unbalanced force downwards. So we already know there must be an unbalanced force downwards, yes, or a resultant force downwards. So automatically got 1 mark just by realizing what they're getting at. The volume of the air, they tell us, has decreased in the diver, yes. So the density or the weight of the diver increases, yeah. So the density of the air increases, the amount of water in there increases. So the diver, remember, is all of that bit together. So the weight increases. So remember, we're talking about forces. This question is about forces. So weight is now greater than the upthrust, yeah? And that's why it moves down. So you have the unbalanced situation here. So again, it's about unbalanced forces. And the resultant force is downwards, therefore the object will accelerate downwards, okay? That's question 13. 3 markers. So the beginning of the paper, they go through quick questions. This is the first one where it's multi-part. So a child's slide has a vertical height of 1.7 meters. As shown, so it's gone there, but you can see it's not a straight slide. The child starts from rest again, 0 at the top, and moves down the slide. The resistive forces acting on the child can be ignored. So again, we have to ignore the resistive forces, otherwise we can't do the mathematics simply. Explain why, it says. So we're talking about an explain. The equations should not be used to determine the maximum speed of the acceleration. So resistive forces have been removed. So now we've got to explain why does physics not work in a simple way. So in this case, it's because there is not a constant acceleration because it's not straight. Yeah, if it was straight, you could use constant acceleration formulated by resolving. So over here it's less steep, over here it's more steep, and then it gets less steep. So the steepness varies. The steepness there varies, faster here, and then it'll slow down again. So it's not a constant acceleration. So that's the first thing you need to get in your minds. You should consider the shape of the slope. Well, the slide does not have a constant steepness or a constant gradient. It varies, okay? These are the points you should be making. There's one mark. All right, so the acceleration will vary, okay, with the steepness of the gradient. To use the equations of motion, the acceleration must be a constant. So remember, these are constant acceleration equations of motion. If they're not constant acceleration, you can't use them. The next question is really applicable to the rest of the next part is applicable to the rest of the question, and you need to understand this, and this is how I would solve it. The child has a mass of 24 kilograms. You don't need to know the mass, yeah, to be able to work out the maximum speed, because to determine the maximum speed of the child, well, at the top of the slide, the child has gravitational potential energy here, which is mg times delta h, the height between the difference between here, the 1.8. There's your delta h. At the bottom, the child's going to have kinetic energy, which is half mv squared. The m is the same. So the gravitational potential lost here is the kinetic energy gained there. So you equate them and you'll find the masses just cancel out. So we don't need to know the mass, and you will see that this will help you with the final part of the question as well. So once you know what I've just shown you on the diagram, the loss of GPE is the gain in kinetic energy, equate them, cancel out the masses, v squared will be equal to 2gh. So the square root, therefore v will be equal to the square root of 2gh. Yeah, so you do that, you square root it, and you'll get 5.77 meters per second if you're using 3 significant figures. And can you put it down to 2 significant figures? Why not? Because they basically, the only thing they've given you is height. This is 3 significant figures, this is 2 significant figures. So 2 or 3 significant figures is applicable to this question. Okay, so that's question 14 first part. And then B, that says the 2 slides, X and Y, have slightly different profiles. They both still have a very steep bit here. This one's got the shallow bit there. And it says X is longer than slide Y. A child moves from rest down slide X. Yes, so height against length these graphs are, and reaches a maximum speed of Vx. And the second child moves down slide Y and has a maximum speed of Vy. The child on slide Y has a greater mass than the child on slide X. But remember, mass has no effect. Yes, what I showed you. The resistive forces acting can be ignored, and mass can also be ignored, and that's what the question is about. Explain how it varies. Well, if we know the mass doesn't vary, we know this equation still applies. See my previous answer. That means in both cases the height is the same. If the height is the same, gravity is the same, 2 is the same, the final velocity will be the same. And that's how you got to get the 3 marks. And let's have a look. This is question 14. So just to show you where they give you the marks for 14b, have a look. You can stop the video and you can mark your own to see if you've got the points listed. Okay, so that's question 14. Question 15 is a student investigating small ball bearings falling through a liquid to determine the viscosity of the liquid. State the conditions needed for Stokes' law to apply. It must be moving at a relatively slow speed. Yes, because remember, Stokes' law is F equals 6 pi r eta v. R means it's spherical. Yeah. So it must be spherical, moving at relatively slow speed, because if not, the viscosity causes turbulence, and the equation doesn't apply if it's turbulent. So it must be laminar. So you can say flow must be laminar or not turbulent, and that's due to the fact that it's spherical and moving at slow speed. So you could also say it must be spherical. Okay, but we've already know it's spherical because it's a small ball bearing. Therefore, it is a spherical object. Okay. Then it says complete the free body force diagram for this ball bearing when it's falling at terminal velocity. Well, terminal velocity means constant velocity, so constant velocity means Newton's first law because it is a balanced situation. Okay, so once we have a balanced situation, you know the up and down forces, drag and up thrust upwards, so must be equal to the weight. So if you move the up thrust and put it up there, the length of these two arrows must be equal to the weight downwards. Okay, so the length of arrows is important in making sure you get the 2 marks. Okay, visually they will check that you've got them roughly right, so make sure you're aware of that. Okay, so that's the beginning of question 15. So you now know the concept. Well, here's the maths. Okay, so once we know that, yeah, we have to equate these forces. Weight is equal to up thrust plus drag. That's where the central theme of this question is. So let's go through it. Student thought that the liquid she used might be glycerol. Okay, so that's the hypothesis. She made the measurements to determine the terminal velocity of a ball bearing. You don't need to know how, but this is a core practical. So you do need to make sure you've looked up viscosity as a core practical for your Unit 3 exam as well. The terminal velocity was measured to be this, 3 significant figures. So here they're giving us 3 significant figures. 3 significant figures, data. Deduce whether the liquid she used was glycerol. So they're giving us all this data, okay? And so you have to see if you get this value for glycerol. So here's the value of glycerol, viscosity. So you want to work out the viscosity, okay? You're not going to use this, you're going to determine it, okay? So they're giving you density of glycerol, they're giving you the radius of the ball, yes? So why do we know that, need that? Because it comes in one of the equations, doesn't it? Weight of the ball bearing is known. So we know weight already, okay? The weight of the ball bearing is given to us. Again, they're giving us 3 significant figures there. So we know the weight. We have to work out the upthrust and we've got to work out the drag. So to calculate the volume of the ball bearing or sphere, and if you do that, you'll see that the ball bearing from the radius will come out to, you put the r cubed in there, make sure you change it to meters cubed, and obviously that's the only thing you need to do. You'll get this to get the volume. Why do you need the volume if you already know the weight of the ball bearing? Because upthrust is the loss of weight, yeah, and the loss of weight is the amount of fluid that the ball bearing displaces. So if you know the volume of the ball bearing, that's how much glycerol it will displace, or fluid it will displace, whatever it is. We want to work it out. And if it's glycerol, the density would be that. So we know the volume, and if you know the volume, you can work out using density equation. You can then work out the mass using this volume. Yes, so you put this volume in here, multiply by the density you're given, and you'll see this is the mass. You then need to work out as a Newton, yes? So this will become the upthrust. So the upthrust is the volume of the ball bearing, which is equal to the volume displaced, times the density of the fluid, which we've given here, multiplied by g. When you put all those in, you'll find that the upthrust is equal to this value. So you'll get a mark for working that out. So now we know the upthrust. We know the weight. We want to work out the drag. So do you agree then the drag will equal weight minus the upthrust? So weight, once again, is given to us here. Upthrust we just calculated as the weight of fluid displaced. So here we got 3 significant figures again. So if you take away the weight from the weight, you take away the upthrust, which we just calculated. This is 10 to the minus 3, this is 10 to the minus 4. The mark scheme, if you look at it, they've actually done it the wrong way here. This is corrected. So this will be the difference. So we now know that the drag force must be this size. What else do we know? We know 6, we know pi, we know the radius, and we know velocity. We want to see what does this give us as viscosity. So you put the numbers in. The viscosity will be this divided by all the other terms, 6 pi. And this is 2.3 times 10 to the minus 3. 2.3 times 10 to the minus 3 is the radius. Yeah, so we're using that again for the viscosity. So we use it to work out the volume, and we're using it for the Stokes law. So this is Stokes law, and this is the velocity that was given to us at the top of the page. So we're given that. You put the values in, you'll see what you get, and if it's close to the value here, yeah, then you have proven that it is glycerol. So we're looking for the answer. I didn't do the calculations, so I'm going to cheat and look at the mark scheme. We're on question 15, yeah, and they've come up with the value at the bottom of the page of point. So when they've done the same calculation, they come up with the glycerol as being 0.943 Pascal seconds, yeah. So once you do that, so if I put that value in, the answer comes to 0.943 Pascal seconds, and then you've got to say, does your calculated value equal the one provided in the data above? Let's have a look. So this is the question mark. You then need to deduce whether the liquid was made of glycerol. So you put that value in there, and you'll see that it is very close. They got 934, you got 943. Now, you could work out the percentage difference, yeah, between them, and you'll see that it's tiny, okay? So you've got to write a conclusion for the final mark. So I haven't done that, okay? So you would say, in the mark scheme, they've put eta 0.94 is approximately equal to 0.93 given, so a valid conclusion based on the comparison between them, okay? So that's what you've got to say. Yes, it is. I conclude that it is made the same thing. And here's where they made a mistake in the mathematics of the weight minus, this is the weight, so it should be the other way around. Okay? Looks like it's just a typing error. Okay, so that's the end of question 15, and that's when I'm going to end the first part of this video, because I've got another session I've got to do in a few minutes, and I'll do the last part of this paper in the follow-up video. Okay, well, thank you for watching. I hope you found it useful. Make sure you do corrections to your own script, and remember, you can actually ask the exam board to send you your script if you're doing a retake, so you can see where you've made a mistake. So please like and share the video with your friends if you think they'll benefit from watching this before next week's retake exam or the May exam for Unit 1, and subscribe so you know when future videos are uploaded. Thank you very much. Hopefully see you soon. Bye.